is long answer question ची answer की 4 mark is first question using differential equation of linear SHM. हॅलो फ्रेंड्स, ही आहे महाराष्ट्र शासनाने शालेय शिक्षण व क्रीडा विभागाने जी 2023मध्ये क्वेश्चन बँक फिजिक्स या विषयाची पाठवली होती. त्याची आज आपण आन्सर की बघणार आहोत. ऑसिलेशन चॅप्टर चालू आहे. आज आपण लॉंग आन्सर क्वेश्चन बघणार आहोत. चला तर मग लॉंग आन्सर क्वेश्चन पाहूयात. हे लॉंग आन्सर क्वेश्चन 4 मार्कीच एकूण 10 आहेत. याची आन्सर आपण पुढील प्रमाणे PDF स्वरूपात बघूया. आहे लॉंग आन्सर क्वेश्चनची आन्सर की 4 मार्क इज फर्स्ट क्वेश्चन युजिंग डिफरेंशियल इक्वेशन ऑफ लिनियर SHM. Obtain an expression for acceleration, velocity and displacement of simple harmonic motion. Answer. First, expression for acceleration in linear SHM. A. From differential equation, d square x divided by dt square plus omega square x is equal to 0. d square x divided by dt is equal to minus omega square x. Equation first. B. But linear acceleration is given by d square x divided by dt square is equal to A. Equation second. From equation 1 and 2, A is equal to minus omega square x. Equation third. Equation third gives acceleration in linear SHM. Second, expression for velocity in linear SHM. A. From differential equation of linear SHM, d square x divided by dt square is equal to minus omega square x. Therefore, d by dt into bracket dx by dt is equal to minus omega square x. dv by dt is equal to minus omega square x since dx by dt is equal to v. Therefore, dv divided by dx into dx divided by dt is equal to minus omega square x. Therefore, v into dv by dx is equal to minus omega square x since dx by dt is equal to v. Therefore, v into dv is equal to minus omega square x into dx. Equation 4. B. Integrating both sides of equation 4. Integrate v into dv is equal to integration minus omega square x into dx. V square divided by 2 is equal to minus omega square x square divided by 2 plus c. Equation 5. Where c is the constant of integration. C. At extreme position, x is equal to plus minus a and v is equal to 0. Substituting this value in equation 5, 0 is equal to minus omega square a square divided by 2 plus c. Therefore, c is equal to omega square a square divided by 2. Equation 6. D. Substituting equation 6 in equation 5, v square divided by 2 is equal to minus omega square x square divided by 2 plus omega square a square divided by 2. Therefore, v square is equal to omega square a square minus omega square into x square. Therefore, v square is equal to omega square into bracket a square minus x square. Therefore, v is equal to plus minus omega under root a square minus x square. This is required expression for velocity in linear SHM. Third, expression for displacement in linear SHM. A. From a differential equation of linear SHM, velocity is given by v is equal to omega under root a square minus x square. Equation first. But a linear motion v is equal to dx by dt. Equation second. From equation 1 and 2, dx by dt is equal to omega under root a square minus x square. Therefore, dx divided by under root a square minus x square is equal to omega into dt. Equation third. B. Integrating both sides of equation third. Integration dx by divided by under root a square minus x square is equal to integration omega into dt. Therefore, sin inverse into bracket x by is equal to omega t plus phi. where alpha is the constant integration which depend upon initial condition phase angle. Therefore x by a is equal to sine into bracket omega t plus phi. Therefore x is equal to a sine into bracket omega t plus phi. This is required expression for displacement of a particle performing linear SHM at a time t. Question number second. Define ideal simple pendulum and obtain an expression for its periodic motion. Answer. An ideal pendulum is a heavy particle suspended by a massless, inextensible, flexible string from a rigid support. Expression for a time period of simple pendulum. First, let m be the mass of the bob and t be the tension of the string. The pendulum remains in equilibrium. The position OA with the center of gravity of the bob vertically below the point of suspension O. Second, if now the pendulum is displaced through a small angle theta called angle amplitude and result it is beginning to oscillate on either side of the means equilibrium position in a single vertical plane. ही आहे रिजिड सपोर्टची डायग्राम, सिंपल पेंडुलमची डायग्राम. हा आहे रिजिड सपोर्ट, हा एम जी साइन थीटा आहे, हा एम जी कॉस थीटा आणि एम जी. Third, in the displacement position, into bracket extreme position, two forces are acting on the bob. A force T due to tension in the string directed along the string towards the support. B weight mg in the vertically downward direction. Fourth, at the extreme position there should be maybe any net force along the string. The component of mg can only balance the force due to tension. Thus, weight mg is resolved into a two component. A. The component mg cos theta along the string, which is balanced by the tension T. B. The component mg sin theta perpendicular to the string in the restoring force acting on mass m tending to return its equilibrium position. Therefore, restoring force F is equal to minus mg into sin theta. Fourth, as theta is very small, theta is less than sin theta approximately theta degree. Therefore, F is approximately minus mg theta from the figure. For small angle, theta is equal to x by L. Therefore, F is equal to minus mg x divided by L. Equation first. M as g and L are constant. F is directly proportional to minus x. 7. And thus for small displacement, the restoring force is directly proportional to the displacement and oppositely directed. Hence, the bob of a simple pendulum performing linear SHM for a small amplitude. The period T for oscillation of a pendulum is given by T is equal to 2 pi under root omega is equal to 2 pi under root acceleration per unit displacement using equation first. F is equal to minus mg x by L. Therefore, ma is equal to minus mg x by L. Therefore, since f is equal to ma, therefore a is equal to minus g x by L. Therefore, a by x is equal to minus g by L is equal to g by L in magnitude. Substituting in the expression for t is equal to 2 pi under root L by g. This is given the expression for the time period of a simple pendulum. Third, deduce the expression for kinetic energy, potential energy, and total energy of a particle performing SHM. State the factor on which total energy depend. Answer first. Expression for the kinetic energy. A. Consider a particle of mass m performing a linear SHM along the path mn about the mean position O as shown in figure. Energy and SHM ही डायग्राम आहे. B. At a given instant, let a particle be at P at a distance x from O. C. Velocity of the particle in SHM is given as V is equal to omega under root A square minus x square is equal to A omega cos into bracket omega t plus phi, where x is the displacement of the particle performing SHM and A is the amplitude of SHM. D. Thus, the kinetic energy AK is equal to 1 half mv square is equal to 1 half m omega square into bracket A square minus x square. Equation first. 1 half k into bracket A square minus x square. This is the kinetic energy at a displacement x. E. Also, at a time t, kinetic energy is AK is equal to 1 half mv square is equal to 1 half ma square omega square cos square into bracket omega t plus phi is equal to 1 half k square cos square into bracket omega t plus phi. Thus, with the time it varies as a cos square theta. Second, expression for potential energy. A. The restoring force acting on the particle at a point P is given by F is equal to minus kx, where k is the force constant. B. Suppose that the particle is displaced further by an infinitesimal displacement dx against a restoring force F. See, the external work done dw during this displacement is dw is equal to F into bracket minus dx is equal to minus kx into bracket minus dx is equal to kx dx. D. The total work done on the particle to displace it from O to P is given by omega w is equal to integration 0 to x dw is equal to 0 to x kx dx is equal to 1 half kx square. E. This work done is stored as the potential energy EP of the particle at displacement x. Therefore, EP is equal to 1 half kx square is equal to 1 half m omega square x square. Equation second. F. At a time t, therefore EP is equal to 1 half kx square is equal to 1 half k square sin square into bracket omega t plus pi is equal to 1 half m a square omega square cos square into bracket omega t plus phi. Thus, with the time it is various as sin square theta. C. Velocity of the particle in SHM is given as V is equal to omega under root A square minus x square is equal to A omega cos into bracket omega t plus phi, where x is the displacement of the particle performing SHM and A is the amplitude of SHM. D. Thus, the kinetic energy AK is equal to 1 half mv square is equal to 1 half m omega square into bracket A square minus x square. Equation first. A is equal to 1 half k into bracket A square minus x square. This is the kinetic energy at a displacement x. Also at a time t, kinetic energy is AK is equal to 1 half m omega mv square is equal to 1 half ma square omega square cos square into bracket omega t plus phi. is equal to 1 half k square cos square into bracket omega t plus phi. Thus, with the time at a variance as a cos square theta. Second, the expression for potential energy A, the restoring force acting on the particle P, is given by F is equal to minus kx, where k is the force constant P. Suppose that the particle is displaced further by an infinitesimal displacement ds against a restoring force F. The external work done dw during this displacement is dw is equal to F into bracket dx is equal to minus kx into bracket dx is equal to kx dx. The total work done on the particle to give displacement is O to P, given by w is equal to integration 0 to x dw is equal to integration 0 to x kx dx is equal to 1 of kx square. This work done restored as a potential energy P, P of the particle at a displacement x. Ep is equal to 1 of kx square is equal to 1 of m omega square x square, equation second. F at a time t, Ep is equal to 1 of kx square is equal to 1 of k square into sin square into omega t plus phi is equal to 1 of m square omega square into cos square into omega t plus phi. Thus, with the time it is various in sin theta. Expression third for a total energy. The total energy of the particle in the sum of that is kinetic energy and potential energy is equal to ak plus ep. We using equation first and equation second, we get E is equal to 1 half m omega square a square minus x square plus 1 half m omega square x square. E is equal to 1 half m omega square a square is equal to 1 half k square is equal to 1 half m into bracket v max square. This expression is given the total energy of the particle at a point P. For the total energy in SHM is A is directly proportional to first the mass of the particle, second the square of the amplitude, third the square of the frequency, fourth the force constant. B the inversely proportional to square of the period. Question: obtain an expression for resultant amplitude of compositions of two SHM having the same period along the same path. Answer: first, consider the particles simultaneously subjected to two SHM having the same period and along the same path. Let it be along the axis but different amplitude and initial phase. The resultant displacement at any instant is equal to vector sum of its displacement due to both SHM at that instant. Let the two linear SHMs be given by equation x1 is equal to a1 into sine into bracket omega t plus phi 1 bracket complete equation first. X2 is equal to a2 into sine into omega t plus phi 2 equation second, where a1 a2 are amplitude, phi 1 phi 2 is the initial phase angle, and x1 and x2 are the displacement of the particle SHM. In time t, omega is the same for both SHMs. Third, the resultant displacement of the two SHMs is given by x is equal to x1 plus x2 is third. Using equation 1 and 2, equation third can be written as x is equal to a1 sine into bracket omega t plus phi 1 plus in a2 sine into bracket omega t plus phi 2 is equal to a1 into bracket sin omega t cos phi 1 plus cos into omega t into sin phi 1 bracket complete plus a2 into bracket sin into omega t into cos phi 2 plus cos omega t sin into phi 2 is equal to a1 sin omega t into cos omega phi 1 plus a1 into cos omega t into sin phi 1 a2 sin omega t cos phi plus a square a2 cos omega t sin phi 2 is equal to a1 sin omega t cos phi 1 plus a2 sin omega t cos phi 2 plus a1 cos into omega t into sin phi 1 plus a2 cos omega t sin phi 2. Therefore x is equal to sin omega t into bracket a1 cos phi 1 plus a2 cos phi 2 plus cos omega t into bracket a1 sin phi 1 plus a2 sin phi 2. Equation 4. Fourth, as a1, a2, q1, q2 are constant, we can combine them. In the term of another constant r and delta as a1 cos phi 1 plus a2 into cos into phi 2 is equal to r cos delta. Equation 5. And a1 into sine into phi 1 plus a2 into sine into phi 2 is equal to r sine delta. Equation 6. 5. Using the equation 5 and 6, equation 4 can be written as x is equal to sine omega t r cos delta plus cos omega t into r sine delta is equal to r into bracket sine into omega t into cos into delta plus cos omega 2 into sine delta. Therefore x is equal to r sine into bracket omega t plus phi. Equation 7 is the equation of an SHM of the same angular frequency, hence the same period, but the amplitude r can be initial phase delta. It's shown that the combination superposition of two linear SHM of the same period and occurring the angle of the same path is also an SHM. Sixth, resultant amplitude is r is equal to under root into bracket r sine delta square plus r cos delta square, and adding equation 5 and 6 we get a1 into cos phi 1 plus a2 cos phi 2 square plus into bracket a1 sin phi 1 plus a2 sin phi 2 square is equal to r square cos square delta plus r e square into sin square into delta. Therefore a1 square into cos square phi 1 plus a2 cos square phi 2 plus 2a1 into a2 cos phi 1 into cos phi 2 plus a1 square into sin square phi 1 plus a2 square is sin square phi 2 plus 2a1 into a2 into sin phi 1 into sin phi 2 is equal to r square into bracket cos square delta plus sin square delta. Therefore a1 square into bracket cos square phi 1 plus sin square phi 1 plus a2 square into bracket cos square phi 1 to phi 2 plus sin square phi 2 plus 2a1 into a2 into bracket cos phi 1 into cos phi 2 sin phi 1 into sin phi 2 is equal to r square. Therefore a1 square plus a2 square plus 2a1 into a2 cos phi 1 minus phi 2 is equal to r square. Therefore r is equal to plus minus under root a square plus a2 square plus 2a1 into a2 into cos into phi 1 minus phi 2. Equation 8. Equation 8 is resultant amplitude of two SHMs. Question second. Define angular SHM and obtain the differential equation. Angular SHM is defined as the oscillatory motion of the body in which the torque for angular acceleration is directly proportional to angular displacement and its direction is opposite to that of angular displacement. So first consider a metallic disc having from a rigid support when twice it is perform an oscillatory motion which the resultant torque acting upon it for angular displacement theta is tau is directly proportional to minus theta. Therefore, tau is equal to minus c theta. Equation first. Second, the constant of proportionality c is the restoring torque per unit angular displacement. Third, if 1 is the moment of the inertia of the disc, the torque acting on the disc is given by tau is equal to I alpha. Second equation, where alpha is the angular acceleration. First, from equation 1 and 2, I alpha is equal to minus c theta. Therefore, I d square theta divided by dt square plus c theta is equal to 0, since a alpha is equal to d square theta divided by dt square. This is the differential equation of angular SHM. Third, obtain an expression for the particle of a magnet vibrating in a uniform magnetic field and performing SHM. Answer: if a bar magnet is freely suspended in the plane of uniform magnetic field, it remains it is equilibrium when with its axis parallel to the direction of this field. If it is given a small angular displacement theta about an axis passing through the center perpendicular to itself and to the field and released it, perform the angular oscillations. Second, let mu be the magnetic dipole moment and be the magnetic field. In the deflected position, a restoring torque acts on the magnet and that tends to bring it back to its equilibrium position. Magnetic vibrating in uniform magnetic field ही diagram आहे. Third, the magnitude of this torque is tau is equal to mu b sin theta if theta b is small. Sin theta is approximately theta. Therefore, tau is equal to mu b 0. Fourth, for a clockwise angular displacement theta, the restoring torque is in the anti-clockwise direction. Tau is equal to I alpha is equal to mu b0 b theta, where I is the moment of the inertia of bar magnet and alpha is it is angular acceleration. Therefore, alpha is equal to minus mu b divided by I theta. Equation first, since mu b and I are constant, equation first shown in the angular acceleration is directly proportional to the angular displacement and directed opposite to the it is angular displacement. Hence, the magnet performing angular SHM. Fourth, sixth, the period vibrating on the magnet is given by T is equal to 2 pi under root angular acceleration per unit angular displacement is equal to 2 pi under root alpha divided by theta. This is the, by considering magnitude of angular acceleration alpha, T is equal to 2 pi under root I divided by mu b. इथे आपले सर्व लॉंग आन्सर क्वेश्चन संपलेले आहेत. व्हिडिओ आवडला असेल तर लाईक करा, शेअर करा, सबस्क्राईब करा आणि बेल आयकॉन दाबायला विसरू नका, कारण नवीन नवीन अपडेट आपल्या चॅनलवरती तुम्हाला मिळत राहतील. धन्यवाद.